Welcome you all to the Spark Research YouTube channel. This is Dr. Vishan, the Assistant Professor in the Department of ECE. And here is the another session for this particular session, electronics devices. And in this session, we are going to take the contents from Unit 3rd of the PCB electronic system, right? So let's continue to talk about it. That is your power electronics. And so gate, before going ahead, let me tell you, gate isn't cracked in the final year. It's built quietly from your first lecture, one concept at a time. So stay consistent and your future will thank you. So start preparation for your gate 2029. Okay, so here is the syllabus for your third unit. So we will look into the basic building blocks of the power supply. That will include the rectifiers, regulators, and then filters, right? And then we'll look into the SMPS, followed by the some wave shaping circuit and the multi-vibrator, and then some electronics instrument. So question number one is that what is this power what is this power how can we supply the power to the DC power, right? Means our objective is to convert so the block diagram typical DC power supply. So our objective is to convert the AC power supply to the DC power supply. So here this is your AC. AC means alternate current. So current is varying or the voltage is varying, right? From 0 to peak to 0 and peak again the minus volt, right? But here if you will see, this is the DC means the constant voltage or the current. So we have to bring AC to DC. So directly we do not have any luxury to directly convert from DC to AC. So question is that how we'll achieve, right? So this is our target. So how we'll achieve? Step number one, we are using some type of the rectifier. Some type of rectifier means half wave, full wave, multiple types of the rectifier. With the help of the rectifier, we will get output like this. So here you can see no negative pulse, right? No negative pulse in the rectified output, but still it is, the voltage is keep on fluctuating 0 to peak, right? So now we will filter out. So how we'll filter out? Using some technique, and then we'll have the less ripple. Now voltage is decreasing, increasing, but very less. Finally we'll regulate, we'll using the regulator, and then we'll get the final DC voltage. So this is the objective. Okay, so let's see how to do. First, rectifier, we can do the rectifier using, we can have either half rectifier or full wave type of the rectifier. So in half wave rectifier, what is happening? We will get the output, like suppose this is your input. So what will be the output? For the output will be only one cycle, right? So there, here it is zero only, right? So this is the half wave rectifier. So this is your output and here is your input, right? So how is it happening? Because this diode will conduct only in forward direction, right? So here the diode will conduct, and in reverse direction diode will not conduct. So diode will allow to pass your current, and then you can absorb the voltage across this RL, right? This is in the forward case. In the reverse bias case, all voltage will drop across the diode only. So here there is no voltage, so zero voltage, because current is not flowing in reverse direction, right? So the current, mathematically you can write in forward direction Im sin omega t, like because of this, right? And pass, it will pass, and there is no current in the reverse direction. So here it is zero only, right? So here is the final graph. You can check it for your input. So this is your input graph, and here the output. So one waveform, then zero again, one waveform, zero, like that. So now we will find out the IDC and average current, and then IRMS, everything, and we'll find out the how efficient is this rectifier, right? So first get the IDC. So how will get this IDC? So IDC in this region, in this first one cycle region, let's calculate the overall current, right? So here IDC is equal to 1 by twice pi. Twice pi is total time period for this one cycle region, and then Im sin omega t and d omega t. And now this current Im sin omega t is valid only for half region 0 to pi. So integration is from 0 to pi, clear? And then plus it will be, of course, in this region there is no current, so 0. So integrate it, you will get the value Im by pi. Clear? Similarly for RMS, now you can find corresponding to the same. So 1 by twice by RMS means root mean square. So first square, then take average, and then square root. So root mean, that is mean means average, and then square. So here if you again same technique you will use, you will get the IRMS is equal to Im by 2. How to solve? So a square, then I square sine square theta. Sine square you have to convert in the cos twice so that we can integrate. So sine square you can write 1 minus cos 2 theta divided by 2. Now integrate. So 1 integration omega t by 2 and cos 2 sine. Now put the limit 0 to pi again and get the value of Im by 2. So this is IRMS. Now after getting the the average and RMS value, now you can calculate the power. So for DC current already we got Im by pi, so your power will be I square into RL. So this will be your power, and if RL and resistances are there inside and in the forward bias, then you can add all those resistance, right? So current AC power will be how much? I square R again only. So here I is equal to Im by 2, that is your RMS current. So use this and you will get the power. Now finally we will get the efficiency. So efficiency is nothing, DC power divided by AC. So DC power we got, AC power we got. So put here all both of them and then get the value. Here you will get 0.406 divided by this, right? If you will put this RFRS is equal to RL, that will case the maximum value, so that will be the 40.6, right? Similarly you can also calculate the ripple factor. Ripple factor is nothing, the RMS value of AC component divided by the average AC DC component, and you can calculate using this equation, right? Similarly, we can also find out the voltage regulation for our half wave rectifier only. So voltage regulation is VDC without load, no load, and minus VDC full load and divided by VDC full load, right? These are the some equations. Similarly, transformer utilization factor, that is TUF. How will you calculate? So DC power delivered divided by the AC power rating of the transformer, and all these things we have already calculated. You can put it here and you can get the value. Clear? Now we'll talk about the Fuller rectifier. So very similar to the previous one. In the Fuller rectifier, now what will happen? Your both waveform, positive again negative waveform, will also shift to the positive. So both waveform will produce the voltage. So that is called full wave rectifier. So if you'll solve similarly the equations, you will get the IDC is equal to twice of Im by pi. If you remember for half wave rectifier, it was Im by pi, right? And here is the circuit. Here two diodes are there. So in forward biased case, this one will work, forward case. In the reverse case, this one will work, and finally you will get the total voltage across this RL, right? This is working principle. So here is your final output, so you will get the full output, right? So the DC will be here IDC, that that you have to integrate again in between these regions. Very simple to that. IRMS also you can follow the same principle, only the limits will be different. So here limits is 0 to twice pi, and in the half wave case it was limit was 0 to pi, because in half wave case only this waveform was passing, but in the full wave both waveform are passing, so limit will be 0 to twice of pi in this region, right? Similarly, you can calculate the efficiency also, and the efficiency, of course, it was 40.6 for half wave rectifier. So it's a double, that is 81.2. These are the key points that you have to remember. Ripple factor also you can calculate similar manner. Maximum ripple factor is 0.48. Here is the comparison among all the rectifiers. So half wave rectifier is here, the full wave rectifier, and this is another case of the full wave rectifier. Here we are using the 4 diodes in order to form the bridge rectifier. You can pause this video and you can check all the comparison details of the all the Almost if we'll check, then the most of these parameters are almost similar, right? Why? Because both are the full wave rectifier, and if you'll have half of all these, then you will get the half wave rectifier. Now we are moving to the control rectifier circuit. So using the SCR, that is silicon control rectifier. So replace your diode with the silicon, the SCR, and all remaining things are same. So this is half wave rectifier, and here is the full rectifier. So all process are same. So I'm not going to discuss it again. I'm just moving forward. We can go through that. Then full rectifier with capacitor filter. So still we whatever the output we got, that is like this, but again they keep on decreasing increasing. So how will you remove this increasing decreasing like this? So we are going to use the filter, that is RC type of the filter. So with the help of that, now what will happen? Now your output is something like this bold one, right? So now you can see here, now you are moving towards the more DC. That is our objective. So in this case, every filter have the some ripple factor. So ripple factor is this one for your half wave rectifier. For full wave rectifier, ripple factor is this. So you may remember all these. These are the important results. Load regulation, similarly, you can calculate for full rectifier. This is nothing, no load minus full load divided by the full load, right? Already we have discussed. So voltage regulator, how will you design your voltage regulator? Of course, we can use the Zener type of diode in order to regulate it. And how will you use this? So you can either use in the series and the shunt. So here if we are using in the parallel case, that is called the shunt voltage regulator. Here using in the series case, so that is called the series voltage regulator. All remaining terms are same. So controller inputs is there, control and the comparator outputs is there, reference voltage of course, and reference voltage will depends on the type of the type of your general diodes that you are using, and then sampling and hold, that will give you the proper output of a fixed value. Okay, so regulations with the varying input voltage. So here is your Zener diode. So whatever the input voltage you are varying, Zener diode will give a particular fixed output because of the the whatever the remaining voltage will the passing, that will cross through the Zener diode, and it will maintain the voltage at a particular level, right? So you can follow this current rule, that is I is equal to IZ plus IL. So IL whatever passing, that will depends on the I of Z, which is passing through the Zener diode. Okay, so then switching mode power supply is there. Here you can check that what is the requirements here. So the required inputs step down transformer is bulky in our regular the regular power supply that we have discussed in the previous slides. But here it is very easy. So the low transformer we are using, so that is the advantage. And also the large values of the filter capacitors are not required here. So these are the advantage with the SMPS. And also the efficiency is very low in case of the regular power supply, but here efficiency will be higher. So what is the characteristic here? You can check it like how will it develop. So it will longer term on and off. So switching on and off rapidly using the inductor capacitor transformer, and efficiency maybe the over up to the 90% even sometime depending on the SMPS, right? So this will exactly being used to convert your AC to DC. So finally, we have achieved the conversion from AC to perfectly DC using the both the techniques. So SMPS have the advantage. Switching device, here we are using the MOSFET type of the switches so that we can have the switching, and output rectifier filter that will convert the AC to DC. And working principle is that AC inputs is rectified to the DC. DC is chopped at the higher frequency using a switch, right? So we are using the MOSFET type of switch that will hold stuff. Wave shaping circuits, here if we will look into the circuits, here we are using the RC. Here look into that, right? So here RC type of the RC type of this. So this is called the clipper type of circuits, and here diode and your capacitor is there. This is called the clamper type of circuits, right? So in clipper type of circuits, it will clipped off for some type of the inputs, and output you will get to the clipped one. Sorry, these are the differentiator, right? In the left side, differentiator integrator are there, and here clipper and clampers are there. So clipper using the one diode and clamper is being used the one capacitor and one diode. So these are the the circuits, and the clipper circuits you can check here, output is only one waveform, and in the clamper your output will be just shifted, right, up or down depending on the type of the clamper. Integrator and differentiator, like differentiator will differentiate your rectangular function, so differentiation will be the impulse type of function, and integration will give the triangular type of the function. So integrator using the RC type of circuits, and differentiator will also, right. These are also will be accessed like the high pass or low pass type of the filter. So now we'll talk about the multi-vibrator. So multi-vibrator is an electronic circuits used to implement a variety of the simple two-state system. It consists two amplifying devices cross-coupled by resistor and capacitor, causing one stable state resulting in a continuous oscillation between the two states. So what are the types? So basically we'll have the three types. Here you can check two transistors are there. Both transistors have the base terminal which is directly connected to the the collector of the second one, right? With the help of the the two capacitor. Okay, so the collector coupled stable the multi vibrator using two identical NPN transistor Q1 and Q2. It is possible that RL1 and RL2 both are equal, right? And also not only this C1 C2, both the capacitance may also be equal. In this case, circuit is known as symmetric or stable multi vibrator. So the transistor Q1 is in the forward biased by the VCC power supply through resistor R2, right? And similarly the transistor this one Q2 is the forward biased by the one VCC power supply using the R1. Okay, and so the output of the transistor Q1 is coupled, and output of your transistor Q1 is coupled to the input of the transistor Q2 through the capacitor C2. Similarly, output of the transistor Q2 is coupled to the input of the Q1 through the C1. So major types is that your astable, monostable and bistable. Astable means no stable state, and monostable one stable state, bistable both stable state. So this is also one short and two flip-flops. So bistable is also looks like flip-flop. It will give the output something like flip-flop output. So this can also store the the information. So that is why this have the memory element. Others doesn't have. Here is the circuits for astable, bistable, and the monostable, right? So you can check the differences here. The key concept that for astable, no stable states, and naturally it will oscillate. All are the oscillator only. It will have the some type of the the waveform generation, right? And applications, of course, it can use clock pulses in the digital logic. Monostable, it is having the one stable state, and application is creating the precise time delay pulses. And the bistable, of course, this will be the act as a flip-flop, means it can store the energy. Both have the stable state, and of course it will have the memory, right? So these are the major crux. And also these type of the circuits easily you can draw using the IC 555. Here you can see IC 555 is connected with the two resistor R1 and R2, and that is the circuit for your stable. Similarly here, if it is connected only one R and C, so this is forming the monostable, and here you are connecting with the single one, and that is the structure for bistable type of the circuit. Now we'll look into the some electronics type of the circuit. So here ammeter is being here. So ammeter is nothing. This is your the in order to measure the current only. This is the one type of the ideal ammeter. So how will you connect? So connect in series here likewise. And so practical of, and how will you design it? So permanent magnet moving coil, PMMC. So with the help of this technique you can do. So equation is your tau torque is equal to BA IN. I is your current, N is your number of turns, A is the area, and B is the magnetic flux. Right. So depending on the amount of current which is flowing through the circuits, the deflection it will occur. So you can measure the amount of the deflection using the amount of the current. That is why this is being used as a current meter, that is ammeter. Similarly, we can design the potential meter, that is voltmeter. So only the thing is that you are going to use in the parallel instead of the series. So remaining all things are same. Now digital multimeter, the combination of both only. Digital multimeter is being used to measure the resistance by applying a known current from an internal resources. And so here is the block diagram. Let me show you the block diagram for your schematic diagram for CRO. Now we are moving to the CRO. You can check the digital multimeter, combination of both digital ammeter, voltmeter. CRO is nothing that is your cathode ray oscilloscope. This is being used to display the voltage or current or any waveform, right? Primary function of time. It will depends on the movement of the electron beam. So this is your electron beam, and once the electron beam they start to propagate the electrons. So here you can see the vertical direction, there will be deflection in the electron because of the electric field, and then the two plates are there, so that will deflect on the that another axis like x-axis or y-axis using the magnetic plates. So electric plates are there, magnetic plates, so totally electrons being dispersed throughout the fluorescent screen, right? So this is your phosphorus screen is there. So here it will convert into the the electron energy to the light energy. So you can, in that manner, you can observe the waveform, right? So this is the working principle. A spectrum analyzer, you can check. This is another technique to observe your waveform. This is nowadays using these are using. So a spectrum analyzer comes in a two basic one. The varieties sweep twinned and the real time sweep twinned are the most common methods. So here you can also draw the oscillators using the mixer, band pass filter, and demodulator. And so in this way we can they use the CRT display to display a waveform. Energy meter, similarly we can use the the power energy is equal to power into time. So power already that is V into I. So you can go through these just these are the very basic things. Power meter V into I. So after measuring the voltage and current, you can measure the power, right? Distortion meter, that is being used to measure the distortion in an electrical circuit, typically an audio signal. Distortion in any advantage changes in the waveform of a signal compared to the original input signal, right? So here you can see if distortion is there, how will you measure? So TST, that is you can measure it using the square root of d2 square like that, and so harmonic details are there, right? So some questions are here. You can check and go through these questions since time is running out. So I'm leaving with these things. You can solve the questions. These are the based on the like the type of the filters that we are using. This is the one of the important the slides where you can check the what is the ripple factor for L type of circuits, C type of circuits, LC type of circuits, and pi type of the filter, right? Stable multivibrator type of circuits, how will you find out the time? So here is the one of the important equation, that is time constant. You can calculate using the T is equal to 2 into 0.693 into RC. For a stable, this is once you will calculate the time, then easily you can calculate the frequency, and time will be here instead of R here 0.693 into RA plus RB, since two different, and duty cycle always will be less than greater than 50% for any type of multivibrator. So play today for stay healthy tomorrow and learn for a lifetime. Thank you.